Okay, so I just don't want you to get bored. As usual, I always give theoretical introduction about the topic, and so to get you ready, and we'll do some code reading. But you guys know my method of teaching. I always finish by numerical example, which puts everything together in one container. So just please be patient. I know some of you, these discussions of the theory, it's very important for them to understand really the in and out of the column design. But I'm asking you for some patience. Okay, anyway, as we said before the break, we talked about the importance of ties in the column, and I'm kind of iterating this one more time. So here I have my square column, and you can see the ties. The ties are spaced at a spacing that we will discuss later on. But really, the importance of the ties, not really for columns. I know they increase the shear capacity of the column, but why do we add them to every single column, even column has a very little shear force, is to simply prevent the vertical bars from buckling for the total length of your column. Yes, the column can, the vertical bars can buckle, but guess what? It buckles on this length between the ties, not on the full length of the vertical bars. And I will show you later on in another slide how the tie itself will be affected, which means if my bar is trying to go this way and this bar is also trying to go this way, what's going to happen to my tie? Okay. And so the next one is next slide is about something called spiral columns. And when you look at the elevation of the column, you will understand what does it mean. It's a continuous bar that we make it like a spiral and confines the vertical bars. It serves the same purpose as the ties. Whether you make it ties or a spiral, both of them, what they do is they are trying to prevent the buckling of the vertical bars on the full length, rather than buckling only in between the spiral or between the ties. Really, what's important for me is this. This slide here is very, very important. The question is, yes, the ties, what they do is they are trying to prevent those bars. Watch this, please. So I'm going to mark the bar and mark where the bar is wanting to go. So all those bars are trying to go and buckle to the outside, not to the inside. Now, let me ask you, if the bar itself is trying to buckle to the outside, what kind of forces will happen to the tie? Not the bar, to the tie. If those are trying to go out to the outside, what happens to the tie? What do you think?
Tension, tensile forces.
That's exactly what's happening. Same as if you have a container that's full of hydrostatic pressure. So then the membrane of the circular container will have a tension. That's correct. But remember, this applies mainly for circular columns. Now, when you think about square column or rectangular column, it will be different. If we have bars in a square column, we have bars on the corner only. See what happens? Those bars, they are trying to go to the outside, same, no change. And this will cause also tension on our tie. How about if I have bar here in the middle and this bar is trying to buckle to the outside? What do you think? Is it going to be only tension or something else? I'm just trying to show
will it have
you.
shear as well?
Excuse me?
Will it have shear as well?
So first of all, the corner bars will cause tension. Look at the idea here. If they are trying to buckle to the outside in those red arrow direction, they will cause tension to the tie. But what I'm saying here, if you have some other bars, not on the corner, but this way, this way in between the corner bars, what happen is, yes, they will have shear, but really what they have is they will bend. They will bend. Something I want to make it clear for now. Now, what do you think about the tie? The tie typically it's 10M, which is like the 10M bars is good in bending more or in tension more. Okay, I'll say it again. I know my question is not clear. Now, those ties, they are made out of 10M bars. Is it easier to bend them or easier to put them in tension? Which one, which is stronger for the tie? Tension, they resist more in tension or more in bending?
They resist more in
I
tension,
think
right?
Yeah, I mean, so thank you so much, Martin. The resist or Brody, I'm not sure about the I don't see your picture, but uh, really the answer is they are really good in tension, very good in tension, but they are so weak in bending. I'm gonna give you an example, a kind of extreme example. Take a hair strand. Take one of your hair strand. I know you will do that anyway in my class and Corwin's class. Doesn't matter. But take one hair strand, try to pull it in tension. It will be very hard for you to break it. But to try to bend it, it is very easy to bend. That's why this is a really good discussion that we'll discuss one more time later on. At this point of time, please understand if you have a circular tie, that's great because simply it is all the time it's under tension, no bending. However, once our column is a square or rectangle, so it will have tension plus bending, and this is a good discussion that we will have later on next class. Now, one thing I want to mention that spiral it works only if you have a circular column. Do you agree? Can we get like a square column and make it spiral?
No.
Spiral?
No.
No, huh? So let me tell you. So every spiral column is a circular column, but not every circular column is a spiral column. Here is now you're gonna pull your hair, huh? Every spiral column is a circular column, but not every circular column is a spiral column because simply we can make a circular column and we can still make ties like at specific distance. Can I get somebody to agree?
Yeah,
Are you
it
up
makes
for that?
sense.
Yeah,
Yeah, it makes sense.
Okay, so again, I'll say it one more time. Every spiral column is a circular column, but not every circular column is a spiral column. Okay, okay, enough fun. Let's go to the next slide. So here is another theoretical discussion, something called centric, concentric loaded columns, and something called eccentric loaded column. And I know this is, you know about this. It's not the first time you hear about it. Probably you heard about it in steel course. You probably heard about it in statics or maybe strength of material. It is, the point is, here is a cross section of your column. Let's say this is the cross section of my column. And you guys know by now, you're a second year CVT and you're professional, you've done 2 design courses, and you know there is something called center of gravity. Do you?
Yes.
Okay, so the center of the gravity is simply the center of the geometric shape of the cross section. And if we apply the load here, if we apply the load exactly at the centroid or the center of the gravity, in this case, what we call this column, centric or concentric column, huh? Concentric or centric, it means the load is concentric with the center of the gravity of your cross section. Very important because simply, let me ask you, for sure if I apply my force here at the centroid, can you tell me what will be the stress distribution on the cross section? Does it vary or constant? Does it vary or uniform? Any help?
uniform.
It's uniform.
Uniform.
Uniform
Exactly.
constant.
Thank you so much for contribution. But if you apply the load at the centroid of the cross section, yes, the stress will be uniform for the entire cross section of the column. How about if I do this? How about if I take the load application point and I moved it? And I know, what does it mean, Tahir? What do you mean moved it? Do we move the column like the way we apply the load? Please wait, please hold. I'll show you how this happens. But I'm telling you at this point of time, what happens if my load doesn't apply on the centroid rather than offset from the centroid. What happens? First of all, we call this one eccentric column because look at the name, eccentricity, eccentricity. This name is not new. You know about eccentricity from geotechnical, from so many courses in CVT. You know about eccentricity. It is simply the offset. I'm going to dimension the eccentricity on the cross section here to there. This distance called eccentricity, E is E, okay, eccentricity. And sometimes the eccentricity will be only along one axis, or sometimes if if the situation is this, I apply my load here, it means I have two eccentricities, one in the X, another Y, another eccentricity in the Y direction. Like this one will be E in Y, and this one here will be E in X direction. But in general, let's make it simple. You know what? This is called the biaxial. So the load is not applied. It's applied offset in X and Y direction. Let's make it simple. I'm not that mean. So I'm going to get rid of this guy. And then I'm going to move my force from here to there. So this is the point of the application of my load. Now, how this would affect the stress distribution of my cross section? Do I still have the uniform stress all over the cross section, or no, the cross section will have different level of stress? So some points will have more stress, sometimes will have less stress. What do you think?
It
It'll be
is not.
different.
It is not uniformly distributed.
True. So thank you, Jelly. The stress is not uniform. So what happened is we don't get the same stress over the cross section. So some points it will have more stress, and some points will have a stress. And by the way, so you know what happens if I simply move this force very far from the cross section, like here. So this point here will be this will be your EX. What happens in this case?
It doesn't even apply to it.
No, it applies.
It
I
it,
know how
it
can.
it applies, but it only applies for the area where the column is, and it is only it is only like almost half of the load will affect to that column.
Guys, you're not following, I guess. Listen, so Mahdi is saying, is saying a statement which simply surprised me. So Mahdi is saying if we apply the load here, which means it's outside the cross section, it means my column will get nothing. Okay. I mean, I don't blame you. I'm gonna explain more, and hopefully this explanation will give you a better insight. So okay. So let's look at this here, the situation here. Okay, you have a column, and then outside from the column, so outside from the column, we extend a cantilever. From the column, extend the cantilever. And so this typically, you will see this shortly in my class. This is typically for overhead crane. If you have an overhead crane, so this column has to go and carry the roof. And on the same time, we have a crane, and the crane will simply place the load here. Okay, so the crane will simply place the reaction at this point here. Okay, you can see the force is outside the cross section. Okay, so the force outside of the column. Does it mean that the column will simply say, I don't see you, crane, you're outside, I'm not going to carry you, fall to the ground? What do you think?
Well, no, because now it has to support that cantilever, right?
Yeah, so the thing is here, this is what I'm trying to say here. If the load, even remember the cross section is here, huh? So this is from this point to this point, this is the cross section, right? Which is simply here. This is the same cross section here. So even the force is outside the cross section, it doesn't mean that the force doesn't place a stress on your column. The thing is, guys, here what I'm trying to add is there is something called the small eccentricity, and there is something called the big eccentricity. The small eccentricity, it means your entire section will have the same kind of stress. So it's compression and compression, tension or tension, but it's different. What does it mean? It means if I show you the stress distribution, so it will be something like that. So will be the stress, will be here much, and here will be less, and simply the stress will be this way, will be more stress on one side, less stress on one side by both of them They are of the same type, like both of them are compression or both of them are tension. Okay. How about if my force is very far? The eccentricity is so big. What does it mean? Guess what? This what happens. It means one side will be in tension and one side will be in compression, if you guys follow. Is that something easy or difficulty? You've done this in your soil classes. Remember when, I guess when Brian told you that the force has to be within the middle third of your section so you don't get tension on one side. Did he say that at some point?
It's been a while and I don't have Brian.
Okay, I bet you that he said that when you think about a foundation or footing that simply the force is not in the middle, or maybe a foundation that has a moment on top of it, it causes one side to be in a higher stress and the other side will be in less stress. What we don't want to see is a tension on one side. And that's why the force, it has to be within the middle third of the section, which means I'm going to dimension it on my section. So this is the middle third. This is the middle third of your section. For example, if this is 200, okay, 200 mil, and so this will be 600. If you are within the middle third, anywhere if your force is within the middle third, it means your entire section will have the same kind of stress. It will be all of it is compression, or all of it will be in tension, but not tension and compression at the same time. Anyway, again, I'm not going to focus for this much at this point of time. Really, what I want you to know is there is something called centric column, where the load is applied exactly at the centroid of the cross section, and there is something called eccentric, where the load or the force is pushed from the center by a distance called E, eccentricity. Let me ask you, which one you think is more realistic? Which one you think you will always encounter in practice? You think that every day when you design, all your column will be centric, or your columns will be eccentric? What do you think?
Eccentric. Eccentric.
Of course, that's the answer. Thank you so much. This is the in reality, to apply the load exactly at the centroid of the column is very hard to achieve, and I would say almost impossible. Very few columns that you will see that my column will be centric column. Now I'll give you 3 examples where or what are the sources of eccentricity, and I'm telling you this is one of my beloved question on the final exam. Okay, sources of eccentricity. Okay, so in a moment frame, that's number 1. In a moment frame, we always, our column here, those column, this column and this column here will be eccentric. Why eccentric? Because of the connection between the column and the beam. Because of the connection between the column and the beam, guess what? When the beam is trying to rotate, the column will say, hey, I'm here. I'm going to rotate with you. I'm going to prevent and restrain you from rotation. And because of this restraint, the column will get some bending moment. Are you guys, do you know that? Do you know that in a moment frame, the beam, sorry, the column will get moment?
Yeah.
Okay, because of the connection. If this connection is released or hinged, it means the column will get only axial force. With the rigid connection, when the beam is trying to rotate under the load, it will grab the column and it will apply a bending moment on your column. So here we go. So this column here, this or this one, will have both vertical load like axial force compression in addition to bending moment. And guess what? Whenever we have bending moment, it means we have eccentricity. Okay, now let's go to the next example of what are the sources of eccentricity. Interior columns. If you are in a building and you have interior column, and you guys know the devil is the live load, and I guess I said this several times. Live load, from the name, from the nature of the load, it can move. So we can have one class full of students on the left and right, and maybe the class here in the middle, it doesn't have a live load. And because of this asymmetric situation, what happened is the beam will simply bend this way. Yeah. So this is kind of the tangent to the curved shape, because we have live load more on the right side and less load on the left side, so your beam will rotate around this point. Once it rotates, it will grab your column and apply bending moment on the column below and above. Now, last example, I have 2 examples here, and I think that's what I was trying to convince Mahdi. This is a typical situation in overhead crane. So sometimes here there is something we have in a workshop. We have a crane, and the crane simply what it does, it simply carry car bars or anything like that, and the columns of the workshop, they have to go to the support of the roof, and on the same time, what we do is we have a cantilever out. So we have this cantilever and this cantilever here. And what they do is simply they support the overhead crane. And you can tell this cantilever will simply bend your column, and you can tell here is the load, the reaction from the crane, and here is the centroid of your column, and you can tell there is an E in between them. There is eccentricity between the centroid of your column and where you apply the load. Here is your E. Here is the eccentricity. One more example is precast. I'm not sure if you've been to a precast garage. I bet you if you went to Chinook. So if you go to the Chinook, look at the Chinook at the barcade, and you will see it's simply like that. So every column, there is a haunch or cantilever that comes out from your column, and this cantilever is supporting girders or beam. Same thing, the girder or the beam will drop the load or the reaction at this point, okay, at this point here, and then it's offset from the centroid of your column, and you will get eccentricity, and all those columns are eccentric, okay? Bottom line is, centric column is a very theoretical thing. Eccentric column are the ones that we should design and look after. Now, when it comes to the eccentricity, okay, so I'm going to go a little bit by little bit to kind of develop the idea of how the column will react to the load. So let's start with the centric column. So centric column, as I said, where is the load? Load is P, and something also I want to mention. So far, you've seen 2 letters. You guys remember the letter M and letter V? Letter M and letter V. So what was M? M was moment. MR and M sub F. Okay? Factored the moment and factored moment capacity. Now, in the next chapter, we looked at shear. So we replaced the M by V. So VR, it become the shear capacity of your beam, and VF is the shear, the factored shear applied to your beam. In this class here, what are we using for axial load? So here we go. The axial load is P. We will use letter P for the axial load. So you will see P sub R and P sub F as well, okay? So you can see here, my P, or the axial load, is acting at the centroid, and because it's acting at the centroid, here is the stress, and that's the strain, which you can tell the strain is the same and the stress is the same. Uniform stress, uniform strain. And what happens here is once the load come to the point where the E is equal to 0.002, and you guys know what is this number, huh? By now, you're supposed to remember what is this number, 0.002. This number is the epsilon Y, where the first point of the yield on the rebar. So as soon as the strain become the 0.002, what happens is those vertical bar will start to yield. But still the column will carry more load. And then until the epsilon arrives at 0.0035. And I'm hoping that by now you still remember what this number is. This number is the epsilon C maximum. The epsilon C maximum, which is the maximum strain in compression for concrete. And this will mark the end of the life of your column. So once the strain become 0.0035, your column will simply burst, your column will fail. And that's what's happening for your axial or centrically loaded column. Now, here is some few picture to show you how the column would fail. So this is one failure of a column, and you can tell exactly the importance of tie. Take a look. I probably have a better picture here. Look at what happens here, guys. Please look at what happens. Look at the ties. Really, the bars are buckling, not really on the full length, but looks like few ties. They failed, and because of they failed, you can tell those bars. I'm referring to this bar here. This bar here, you can tell it buckles on more than the distance between the ties. And look at how the ties failed. Actually, to be honest, this is part of a building, and I can tell you 100% the failure of this building was because of an earthquake. So it's very hard to understand, but earthquake, people, they think that earthquake is almost it's a horizontal force. But you will be surprised if I tell you some of the earthquake, they shake the building also vertically, not only shaking the building horizontally, but also they shake the building vertically. And if they shake the building vertically, oh my God, this is crazy, because simply it increases the forces on the column dramatically. Think about it, huh? You are in the elevator. You feel when the elevator is simply going up. If the elevator is going up, do you feel yourself heavier or lighter?
Heavier.
Heavier. How about when the elevator is going down? Do you feel yourself lighter, right? So it's exactly the same thing. When the earthquake shakes this building up and down, the forces on the column will dramatically increase, and that's what causes this building to fail. And some of you may ask, how come the columns failed but the building is still alive? The building is on the right side. You can see still standing. That's just luck. Maybe the earthquake was so short, and as soon as and maybe take for maybe 1 or 2 seconds, and then this what caused this problem. But luckily, because the earthquake stopped, then whatever left from the column still can take the load. Maybe the building, there is no occupant, maybe the building, it doesn't have all the full load, design load, but I promise you, if it has the design load, like all the live load is available, this building simply will collapse. Okay, now this is very simple to understand. So I'm trying to show you right now the kind of equation, how the column, the axial, the centric column will create a resistance. It looks the same as the shear. Do you guys remember VR is equal to VC plus VS? Does anybody remember VR equal to VC plus VS? I think you still remember. It's the same idea. So this number here is how much the column can take vertically, like axial load compression, and this is the contribution of the concrete, and this is the contribution of the vertical bars. And remember, ties, they have no business. And why they have no business? Because simply they are oriented perpendicular to the load application, same as the stirrup. So the stirrup in the column, in beams, does it increase the bending capacity? It doesn't. The stirrup does not affect the bending capacity for the beam. Same here, the tie, as long as you provide the minimum ties, then that's okay, and it doesn't affect your axial capacity of your column. But again, one more time, look at this. So I'm trying here to support a vertical load. Some of it will be supported by concrete core, and the rest will be supported by the steel vertical bars. Okay. Now, it's not very difficult to understand. Here is the contribution of each. This part is the contribution of the concrete core, which is, you remember, this is the phi C, the F prime C. And what is F prime C? Is simply how much, if I say 25 MPa, it means that every square millimeter of concrete can take 25 Newton. Do you guys agree? When I say concrete 25 MPa, it means every square millimeter of my concrete can resist 25 Newton.
Yes.
You agree? Okay, and so why do we multiply by phi c? Why did we ever multiply the f prime c by phi sub c?
To reduce this resistance of the concrete.
Excellent. Does anybody still remember how much is phi sub c?
0.65.
Thank you so much. Okay, so you can tell this is a stress. Okay, I know that nobody, I doubt that anybody will remember the alpha 1 by now because that's too long ago.
0.8. 0.8.
0.8, thank you. And do you ever remember, I know that this is even difficult, more difficult. Do you remember why did we use alpha 1 and beta 1?
That is for the equivalency of the equivalent of the spiral. I mean, not spiral, but what kind of parabolic? Yeah.
Parabolic shape. And you can see we have the same problem here. We have a non-linear relationship between stress and strain, and that's why we used alpha 1 phi c f prime c. And so you can tell that this whole term is a stress. And so what do we multiply the stress by so we can get a force? So this term here is a stress. Let's say at the end we get 10 MPa. It means every millimeter square it can support 10 Newton. How can we turn the stress into a force? We simply multiply by the area exposed to the stress. And the area exposed to the stress is very simple. It's the gross area of cross section minus the area of the steel. The area of the concrete is equal to the gross area minus the area of the steel. Would you agree?
Yes.
Yes. Okay. And then what happens is when you multiply stress times the area, you will get the concrete resistance. And then for the steel, we have, let's say, a few vertical bars. And simply the area of steel is, let's say, we have 4 bars and we have 20 M. So this will give you the area of steel of the vertical bars. So which means the area of the ties is not included. This area here is the area of the vertical bars. The area of the vertical bars. And if you multiply the area of the vertical bars, multiply by the stress, which is F yield, multiply by, I think there is a mistake here, please take a note, and I will correct this one. This is not really phi sub c. Would you agree?
Phi S. Phi S.
Thank you so much. I'm going to take a note. Give me a minute, please. It's on page 14. Okay, so please take a note that this not phi c, this is phi sub s because that's steel, huh? So we multiply 85% times 400, and this will give you a reduced stress. Then you finally multiply by the area of the vertical bars. Then what you get is the capacity of your vertical bars. And what you do is you simply multiply the two of them. Sorry, add, not multiply. Add BRCO and PRSO, and this will give you the BR0. Not very difficult, just the contribution of the concrete, of the steel, and the contribution of the concrete. And so this will give you total resistance. Please take a note that this is phi C, and this is, this is phi S, and this is phi S, not phi C, because that's steel. Okay, finally, the code according to 10.10.4, I just snapped this from the code. The code simply ask for a little bit of reduction of this number here. So not very difficult. If you have a spiral column, then what you do is you simply multiply this number times 90%. So whatever you get from this equation, you multiply by 90% for spiral column. And for tight column, you have to use this equation. I will zoom in. Okay. Now let's look at the equation. The equation, it tells you BR maximum is a number multiplied by BR node, and this number is 0.2, and it's plus. So this is plus, huh? It's not minus. So this is plus 0.002 multiplied by H. And what is H? It's over there. H is the wall thickness or the minimum column dimension. Let's say the column is 300 by something, huh? 300 mil by something. Can I get some help? If H is equal to 300, okay? So let's say H equal to 300 millimeter. Please help me and find for me what should be this number here. I'm going to box it out. So I'm going to draw a rectangle around it. So you take the 300, multiply it by 0.002, and then add to 0.2. What do you get?
0.8.
0.8. And I can tell you something which is kind of will look weird. The minimum we build our column minimum is 300 mil. The minimum is 300 mil. Sometimes we do 250, same as the beam width. You guys remember when I said talk about the beam width? Do you remember when I said about the beam width, the width of the beam? Can we make it 100 mil? Can we do that?
No, it's a minimum of 200 mm.
Yeah, that's, by the way, I have myself built a 200 millimeter and the contractor complained because they cannot do the beam. Guys, why do we say minimum 200 in the beam? We have cover and cover, we have tie and tie, we have 2 bars, and we have a spacing. All of that needs spacing, right? And I can tell you same thing here. Practically, I would tell you minimum 250. But anyway, the code says no matter what you get from this equation, it has to be less than 0.8 BRO maximum. So this combination here, maximum 0.8. So very simple, not very difficult. You have to find your BR0 from this equation, then multiply it by 0.9. That's if a spiral column, and if it's a tight column, then multiply by a number, this number maximum 0.8. So it can be, guys, help me out, please. Let's estimate this number for H equal to 200, and let's do it one more time for H equal to 250, please. Any help?
You got 0.4 for 200.
0.44.
200, yeah. No, just 0.04.
Did you add the 0.2?
Hold on. Yeah, 0.6. That's 0.6.
0.6. And then for 250? 0.7, huh? 0.7.
Yeah,
it's 0.7.
It is 0.7.
Okay, so and this one is going to be if H is equal to 300, so looks like this number is equal to 0.8. You can
That's
tell,
0.8, yeah.
I can tell you most of the column that I built, it's 300 millimeter wide, and we use the 0.8. But can I ask you something? Which one you think it carries more load, spiral or tight column, based on this statement here?
It should be the 0.8. The
spiral
0.8.
Spiral column, we take the BR0 and then multiply it by 0.9. And tight column, we take the BR0, multiply it by 0.8 or 0.6 or 0.7. It depends on the minimum dimension of the column. I'm asking you, if we have 2 columns, one is spiral and one is tight.
Spiral can carry more loads.
Does anyone know why spiral can carry more loads?
Does it have to do with the way it's the way the rings are, like the ties?
Actually, I'll tell you something. The code never said why, but Tahir, that's my opinion. Why the spiral column they carry more load? Because of 2 things. Number one is they confine the concrete core more. Think about the spiral, how it's being laid out, like it's a continuous member that goes like a spiral. And so to me, this confines even more the concrete core. So this will increase a little bit the capacity of your column. Number 2, look at the ties are, if it's tie, the tie is oriented 100%. It's perpendicular to the load application, so they don't interfere. How about the spiral? The spiral, it has something called a pitch angle, so it's always climbing up, and that's why the tie cross section, so the spiral cross section, it contributes a little bit with the vertical members. This is my own explanation. Okay. So anyway, so I'm going to stop in here, and then tomorrow we will have to add on that. Any questions so far?
I have a question about the carrying more load. Would the spiral also, the area steel, would that help?
I'm
Or is it
assuming when I ask the question, which one will carry more, the spiral or the tie, here is my assumption. So we have the same circular column, two circular column identical. They have the same number of rebar, they have the same bar diameter, they have the same concrete, everything is the same. The difference is one circular column is made tight, like a spacing, and the other one is a spiral. Okay, according to this equation, it looks like the spiral will carry more than the tight column. So to make it clear, everything is the same except that one is tight and the other one is a spiral. Are you following, Nicholas?
Yeah.
Okay. Any other question? We have only 1 minute, maybe for another question if you wish. Okay, so no question, and I will see you. I'll see you tomorrow in the morning. And yeah, have a good day. Thank you.
Thanks, Tahir.
Thank you.
Thank you, Tahir.
Thank you.